All right, back at it. Next video. Let's get it going. Okay, so let's just review some of these learning goals that I went over in that last video, which I know that one went a little long. Okay, so just take it in stride, right? Take it one concept at a time. Okay, but what I went over, okay, just to make sure we're all clear, what color do I have? Let's get a yellow. Okay, I think that's right. So, okay, understand the concept of the mole and how to interconvert masses, number of particles, atoms, etc., given a set of data. Okay, that was definitely covered over in that previous lecture. All right, in lecture number 7. Be able to calculate molar mass for a given chemical formula. Yep, we did that as well. Okay. Be able to balance chemical reactions. We definitely did that. And I understand, you're only seeing me do this thing like once or twice in the lecture, and I'm highlighting the learning goal, like, yep, we did it, move on. But remember, okay, you might be in this category. Well, I'm not ready for a test. Or maybe you're even in this category. I feel okay, but I need more practice, right? So remember, use this document as a means of guiding yourself through the material, okay? You can tell by now I go through things a little on the faster side because we do have a lot of content to go through, okay? So I might go through something really fast and then move past it. Make sure that you feel good about that before you move on, okay? And then I think the last thing we talked about, being able to come up with a balanced combustion reaction given any hydrocarbon. So I went through a couple examples, and I noticed, you notice I said CXHY, right? I gave you the example of methane, which is CH4. I gave you the example of propane, which was C3H8. I gave you the example of butane, which was C4H10. And we even did octane, but you didn't know I did octane. That one was C8H18, okay? And more on octane in this video, okay? And so it looks like after one video, I got through all, or half of these learning goals, okay? These other ones, I'm gonna go a little bit slower because there's gonna be a lot of example problems that I work through, okay? But first, I do want to spend just a brief moment talking about the carbon cycle, which you notice wasn't anywhere in the learning goals, right? So this is a little bit extra, but I think this is good stuff for you to know, okay? So, combustion of hydrocarbon, right? We noted that it's any hydrocarbon, CXHY, plus oxygen makes CO2 and water. I think I realized I also neglected to go through this in the last lecture, right? But I hope that this is obvious. G for gas, right? And in combustion, take note of that. These are all gases, okay? And for the combustion, it can be a gas or liquid, so liquid, L. Gases ignite more readily than liquids, and we can talk about why that is later, but certainly I just mostly want you to recognize these symbols. We're going to see them more and more and talk about them more and more as we go, okay? So for example, this AQ stands for aqueous, okay, which means it's dissolved in water. And again, more on that in the coming chapters, okay? So, but what I want you to focus on, what I want you to compare combustion of hydrocarbon, right? Like such as gasoline, okay? And I mentioned octane. Octane is C8H18. That's the principal component of gasoline, octane. Okay, that's what you put in your car to make it go, okay? Look, respiration. Let's look at this reaction, okay? C6H12O6, as it turns out, that's sugar, that's glucose, okay? But look how similar that is. Plus oxygen makes carbon dioxide and water. That's very cool. So everyone breathe with me. And I want you to know that the carbon that you exhale comes from the carbon that you eat. Okay? The carbon that you're exhaling is coming from the carbon that you're eating. That's a very oversimplified version of that, and those of you that are biology majors will go on to learn probably far more than I know about respiration. But I think that's a pretty cool idea, right? That we consume fuel and we exhale the CO2 and the water. And of course, we exhale a little bit of O2 as well, right? But for this idea of respiration, particularly mammalian respiration, right? The carbon that we exhale is the carbon that we consume, okay? And then now let's compare that to photosynthesis. It's the reverse of respiration, okay? So what that means is combustion of hydrocarbon is a source of CO2, okay? Respiration is a source of CO2. So there's a lot of creatures out there in the world that are exhaling CO2, and that's a significant source of carbon dioxide in Earth's atmosphere. Photosynthesis is a sink of CO2. So while all of the mouth breathers like me are pushing out a bunch of CO2, the plants are taking it in and converting it into sugar and energy, all right? So this is kind of an oversimplified view of the carbon cycle. And those of you that go on to do, environmental science classes, you're going to learn a whole lot more about the carbon cycle. The main thing that I wanted to draw your attention to, when we think about all of this CO2 in the atmosphere, right? It's what we call a greenhouse gas, okay? And that CO2 traps heat in it, traps terrestrial radiation. So that's heat that's coming off the surface of the planet that would normally escape out into space, okay? But some of that is trapped. And it's okay that some of that is trapped. We're the Goldilocks planet. We want just a little bit of greenhouse effect is okay. That keeps us nice and toasty. However, with too much greenhouse effect or with too much CO2, that's a bad thing. And what I want you to take note of this, there are a lot of sources of CO2 in the atmosphere. There's a lot of things that produce CO2, like respiration. See, it's making CO2, more respiration. So that's respiration coming from, the animals in the ocean, or respiration coming from animals on the land, like me. You notice here, let's see, number 4 is, let's see here. Number 4 is CO2 that comes off of the land. So this is called detritus. I don't want to spend a lot of time talking about this, okay? What I mostly want to talk about is this, the combustion. And the source of CO2 from combustion is humongous. It's huge. And it's just getting bigger and bigger and bigger with the more human activity there is. And you notice the only thing that really takes CO2 out is photosynthesis. Photosynthesis through marine phytoplankton or just photosynthesis through terrestrial plants, okay? So right now, the sources of CO2 in the atmosphere, particularly from combustion, are far outweighing the sinks of CO2, okay? And even though these things, they might not seem like a lot to us when we talk about, the CO2 right now is about 400 parts per million. So that means for every 1 million molecules of air, only 400 of them are carbon dioxide. So it doesn't sound like a lot. However, the real important thing that's going on right now is because of this, there's imbalance in this carbon cycle. We're producing far more than what can be taken out. And particularly when we note that terrestrial plants are responsible for taking out carbon dioxide, but we're mowing them all down, right? We're cutting down the rainforests. That creates an even bigger issue. Okay, so that's all I'm really going to say about this, at least for now. And I certainly know I probably did not give this any justice at all, so I hope there's no environmental scientists out there like, wow, he just did a terrible job describing that. Again, I just wanted to give you a general overview. And those of you that get into this in your major, you're gonna explore this in a lot of detail. Okay. So let's keep going. Okay. And what we're gonna get into, and particularly, I'm gonna talk about these types of combustion reactions a lot with fossil fuels because I think it's important that we understand how we go from so many grams or milliliters or gallons of gasoline to translate that to how much CO2 is that going to put in the air. Okay. So this is going to be our first little bit on doing what I'm going to call stoichiometry or stoichiometric calculations in chemical reactions. This is going to be challenging. This is going to be hard. Okay. So we're going to take it one problem, one reaction at a time. Okay. So we're back to this reaction that we talked about earlier. So this is the reaction of propane. Okay. And whenever we see a chemical reaction, the first thing that I want you to start thinking about is it balanced? Is the reaction balanced? And if not, before I do anything, I have to balance it. So hopefully you can tell with all these blank spaces, the reaction's not balanced. So we've got to balance it. And as you recall from last time we did that, these numbers were 1, 5, 3, and 4. Make sure you can get to those numbers, right? We did that last time. Okay. And so now this is not so much a question of how much CO2 will this reaction produce, but instead it's how much oxygen will react with 96.1 grams of propane. And so what we're going to start doing, we're going to start really seeing these kind of big, complicated word problems, and we need to be able to calculate any quantity asked from us for a chemical reaction. Okay, so I'll say that again. I want you to be able to calculate any quantity that's asked of you in a chemical reaction. So we have to read this question critically. We have to use some critical thinking to know what's going on. Okay, so it's asking us what mass of oxygen. Okay, well that's going to be my final answer. My final answer is going to be mass of oxygen. Okay, so just tell yourself that. My final answer has to be mass of oxygen. What mass of oxygen will react with 96.1 grams of propane? Okay, hopefully we remember that's the propane. Okay, and hopefully we're also starting to recognize the process. We're going to use the first number I was given first. And in this case, of course, it's the only number, but all the same, it was still the first number I was given. So I'm going to write it down blindly. 9.61 grams of C3H8. That's how we're going to start this thing. Okay? So now what I can do from here is the same process. Down, up, down, up, down, up. So I know what I need right here is grams of propane to make these two things cancel, right? And so what am I going to replace that with? Hopefully you said the molar mass, okay? And if not, then this is why we want to use the molar mass, okay? I can see in my reaction that for every 1 mole of propane, I need 5 moles of oxygen. It's a 1:5 ratio to make this reaction happen, okay? So what I really need to do is convert this grams of propane into moles of propane. So we're going to write that down for reactions with chemical reactions, okay? If we have grams to start with, and I'm going to say grams of reactant, I need to make that into moles of reactant, okay? And I can do that with the molar mass. And to calculate the molar mass, I take 3 times the average mass of carbon plus 8 times the average mass of hydrogen, boop, 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 you should get 44.097. So where does that come from? That comes from saying, I know hydrogen is 1.008 times 8 equals, and that's going to be plus 3 times 12.011 for carbon equals 44.097. That's where that number came from. Okay? So there's that number of grams in 1 mole of propane. And I know a lot of you are just going to want to calculate this thing and stop. Okay, I turned grams of reactants into mole of reactants. Let it ride. Let it keep going. Okay? So now I've canceled that. So now, if I have grams of reactants, I convert it to moles of reactants. Now I want to go from moles of reactants to moles of product. How do I do that? That's a little bit trickier. Okay? So again, the reaction tells me for every 1 mole of propane, I need 5 moles of oxygen. So remember, I still have to do the right order of units. Down, up, down, up. So I want to cancel mole of propane. I want to convert moles of propane into moles of oxygen. Convert moles of reactant into moles of product. Okay? So I'm going to convert mole of C3H8 into mole of O2. Well, how do I know which number to put? Well, my balanced reaction tells me for every 1 mole of propane, it needs 5 moles of oxygen. Okay? So you can put it just as another line right there. Okay? And then now this problem is asking me what mass of oxygen. So finally I can go moles of product into mass of product. And I'm going to use the molar mass of oxygen. I'm going to say 1 mole of O2, right? Because I want the mole of O2 and the mole of O2 to cancel. And I know from my periodic table, each oxygen is 15.999 times 2 gives me 31.998. We'll keep all those digits. Why not? Grams of O2. And then now everything's canceled, and I'm left with grams of O2 in my final unit. So that's going to be the final unit of my answer. So equals grams of O2. Now what about the number? Okay, I'm going to say here 96.1 times 1. I'm pointing it, but like you can't tell where I'm pointing. So 96.1 times 1 times 5 times 31.98. Okay, equals, okay, times 5 equals times 31.998 equals. Now I'm just going to keep that number in there, and I'm just going to say divided by 44.097 equals. And let's see, I don't have any other numbers to worry about here, okay? Just, I could say divide by 1 and divide by 1. And then I recognize the 96.1 is 3 sig figs. So my final answer is going to have 3 sig figs. So to me, that would be 349 with 3 sig figs. 349 grams. So what does all of this mean? Well, what this means is 1 mole of C3H8 needs to react with 5 moles of O2 for both of them to be completely consumed. So think of this as like baking or cooking or whatever, right? It's a recipe, right? If I want to react all 1 mole of my propane, I need 5 moles of oxygen. Well, now that's the exact same thing as saying 96.1 grams of this will react with exactly 349 grams of this. Okay? That's all that we did. We just said if 1 mole of propane needs 5 moles of oxygen, that's the same thing as saying 96.1 grams of propane needs 349 grams of oxygen. All right? So make sure you're able to do that. I'm going to move on to another problem, another example problem, and it's going to be a little bit harder. Okay? So I'll show you how we add on those extra details, those extra layers. Okay? So I'm sorry this is getting cut off. Let me see if I can fix that. Does it recenter? Okay, so I'll just read it from my cheater notes right here. I think you should be able to read it from your own notes, but it says solid lithium hydroxide, and every time I see a chemical name or some useful information, I'm gonna like underline it, right? Solid lithium hydroxide is used in space vehicles to remove exhaled carbon dioxide from the living environment by forming solid lithium carbonate and liquid water. What mass of gaseous carbon dioxide can be absorbed by 1 kilogram of lithium hydroxide? Whoa, that's tough. That's like a word problem from hell. Don't worry, they're going to get harder. Okay, here's how we deal with hard word problems. First, you notice I underlined all of the names of these chemicals. And this problem is especially hard because I didn't give you any formulas. So remember, I told you, you've got to be able to go from name to formula or formula to name. Okay? So let's read it again, but this time let's put this into a chemical reaction. Okay? So it says solid lithium hydroxide. I know you can't read that. I'm sorry, it's cut off. Let me try one more time. Oh, I just made it bigger, but now you can't see what I got going on. Oh, wait a second. Kind of. You can see OLID. Anyways, you can download this file and read what it says. Okay? So let's start there. Solid lithium hydroxide. So hopefully you're able to come up with LiOH. So remember, hydroxide is OH minus, so it's a polyatomic ion, right? The whole thing is OH minus, and lithium is always +1. So lithium hydroxide, cation, anion, okay? And it says solid, so I'm gonna put that little subscript down there, and I want you to get used to putting those phases in. Sometimes we don't worry about putting the phases in if it's not that big of a deal, but when we can see with this reaction, when we have different phases, solid, liquid, and gas, you got to put them in there, all right? So solid lithium hydroxide is used in space vehicles to remove exhaled carbon dioxide. Okay, the lithium hydroxide is reacting with the carbon dioxide to remove it. So that means when something is getting removed, it's a reactant. When something is being formed, right, by forming, that means it's a product, okay? By forming solid lithium carbonate, okay, this one's tough. Carbonate is CO3, 2-, you knew that because you did your polyatomic ions and you made your note cards and stuff, so you're a good student. So you knew carbonate was CO3, 2-. Lithium is still, let me do that again. Lithium is still Li1+. So that means to make lithium carbonate, I need 2 lithiums for every 1 carbonate, okay? And I can write that as Li2CO3, and it said it was solid. Okay. Make sure you can do this. If you're still struggling with this, come talk to me. I'll help you make sure that you're getting formulas put together. So it says by forming solid lithium carbonate and liquid water. Okay, I know how to write liquid water. That's H2O liquid. Okay. So now it's asking me what mass, and I'm going to put a question mark next to the carbon dioxide. What mass of carbon dioxide can be absorbed by 1.00 kilograms of lithium hydroxide? So that means what I'm doing here is I'm saying if I have 1 kilogram of lithium hydroxide, how much carbon dioxide do I need to react with all of that? And maybe what you might also be thinking, did I balance this reaction? No, we got to do that. Okay, so let's balance it. Okay, so what I notice here when I start looking at the stuff that's obvious, I've got one lithium here and I've got two lithiums here. So that means I need to put a 2 here. So that means I got two lithiums, but it also means I added two hydroxides. So I'm going to have to balance the other stuff. And as we go through and look, okay, one carbon and one carbon, two lithiums and two lithiums. So we're all good there. But look, two hydrogens and two hydrogens. So that's great. And then one oxygen plus three oxygens gives me four oxygens. And then now 1, 2, and then look, 2 more, 3, 4. So it's all balanced. So I did that fast. So if you have to pause it and work this out and make sure you can get it balanced, you should definitely do that. Okay? I'm going to move forward. So now, again, what's the problem asking for? Well, the problem, first of all, we'll just say what the balanced reaction tells me. The balanced reaction tells me for every 2 moles of lithium hydroxide, I need 1 mole of CO2. Okay? That's pretty straightforward. 2 moles of lithium hydroxide reacts with 1 mole of CO2. But what's really more useful is if I have 1 kilo of lithium hydroxide, how many kilograms or grams, doesn't matter, maybe we'll keep it in kilograms since the lithium was also in kilograms, right? How many kilos of CO2 do I need to react with that? Okay, so here's what we're going to do. We're going to start with the first number that we were given. We were only given one number in this problem, 1.00 kilograms of lithium hydroxide. Okay? And I need to convert that kilograms to grams because remember in my process, I'm going to go, in this case, mass of reactant to mole of reactant. And to go from mass of reactant to mole of reactant, I have to make it grams because remember the mass on the periodic table is grams per mole. Okay, so I can say in 1 kilogram, there's 1,000 grams. That cancels the kilogram and the kilogram. And now if I look up the molar mass on the periodic table of lithium hydroxide, well, of lithium plus oxygen plus hydrogen, okay, it is 23.95 grams per mole. So I get that from the 15.99 for oxygen, 1.008 for hydrogen, and then lithium is 6.941. Okay, so 6.941 for lithium plus 15.999 for oxygen plus 1.008 for hydrogen, 23. I wrote 95, but you can see it's 23.948. 23.95 is fine. So, but now how do I use that number? Well, look, I've got grams here, so I have to have grams on the bottom, okay? Which means I'm going to say, I know it's going to look goofy to write this upside down, but this is how I have to do it. 23.95 grams of lithium in 1 mole of lithium. And I put that chemical symbol there, lithium hydroxide. I put that chemical symbol there so I know which thing I'm working with. So I just do that as an extra layer for myself. And so now I've canceled grams of lithium hydroxide, and now I've got moles of lithium hydroxide. Okay? And right in my steps, I should have a better infographic for this, but I don't. So mass of reactant goes to mole of reactant goes to mole of product. Or in this case, mole of other reactants. So sorry about that. So I could have converted it to moles of product. But in this case, I was asked, remember, you got to think about what you're asked for. I was asked for how much of this reactant do I need to react with how much of this reactant. And to do that, I have to compare moles to moles. So now I can go down and I can say 1 mole of lithium hydroxide. Oh, but wait a minute. I just wrote 1 kind of blindly because that's how I normally am used to doing this thing. But what does this tell me? This actually tells me 2 moles of lithium hydroxide react with 1 mole of CO2. Okay? So now moles of CO2 is canceled. Mole of lithium hydroxide and lithium hydroxide are canceled. Now I have mole of CO2, and it's asking me what mass of gaseous carbon dioxide can be absorbed, and it didn't tell me what units to use. So since it didn't tell me, I'm just going to actually just stick with grams. That's fine. But I'll show you how I could convert it to kilograms as well. Okay? And so from the periodic table, carbon is 12.011 plus, and look, there's 2 oxygens in CO2, so it's going to be plus 2 times 15.999. When you teach chemistry, you start to memorize all the masses on the periodic table. Okay, so 44, let's call it 44.01. And how do I use that number? Well, I have to go down, and I still have to say mole of CO2. And in this case, it's 1 mole of CO2 because it's the molar mass that I'm dealing with, right? 44.01 grams per mole. Okay? And that gives me grams of CO2. And so mole of CO2 cancels and mole of CO2 cancels. And look, I can let it ride. I can keep going. Because if I did want to make this kilograms, then it's really easy. All I have to do is 1 more line and just say in 1,000 grams, there's 1 kilogram. Okay? And I know what you're thinking. Well, why did I need that? Because look, they're just all going to cancel each other. Okay? And that's true. But because now we have this problem where there was 1, 2, 3, 4, 5 steps, I don't care if I'm writing like redundant information. Okay? So grams and grams cancel, and I'm left with kilogram of CO2. It's okay to be a little redundant because that's going to help me keep track of what's going on. Okay? And so now finally, when I do this calculation, I'm going to say 1.00 times 1,000 times 1 times 1 times 44.01 times 1. So I'm just going to say, to make life easier, 1,000 times 44.01 equals, and now that's going to be divide by 23.95 equals, and then now divide by 2 equals, and then now divide by 1,000 equals, and I get 0 point, and I want 3 sig figs, 0.919 kilograms of CO2, or that would have been the same thing as 919 grams of CO2. Since the question didn't specify what they want, either is fine. But what's useful about comparing kilograms to kilograms, that's kind of neat, right? That like roughly 1 kilogram of lithium hydroxide will absorb about 1 kilogram of CO2. It's technically 0.919, but all the same, that's kind of actually nice to see that it's about the same mass, even though we wouldn't have been able to guess that right away from the mole to mole ratio. Okay? So let's keep going. I'm going to do one more problem in this video, and it's cutting off my stuff there for some reason. Maybe if I like do this or this, I don't know what's wrong with you. Anyways, so I'm going to work through this one more problem, okay? Then I'm going to show you what I consider to be a really, really, really hard problem. I'm not going to do it because we're going to do that really, really hard problem in discussion. And we're not going to do it in discussion until week 4, okay? So I'm a little ahead of the game recording these lectures, okay? So I'll read you the problem. Coke, I know you can't read it, but that says coke is an impure form of carbon that is often used in the industrial production of metals from their oxides. I'm not talking about coke like cocaine. Get it out of your minds, you college students. Okay. Coke is a real thing. Coke is an impure form of carbon. Okay, that's what it is, right? So if a sample of Coke is 95% carbon by mass, determine the mass of Coke needed to completely react with 1.0 ton of copper 2 oxide. Wow, there's a lot going on in this problem. And oh, it's cutting off the reaction. I just noticed that too. Okay, so I'll just rewrite that reaction just so you can see it. It's 2 CuO solid plus 1 carbon makes 2 copper atoms plus carbon dioxide gas, and that is balanced. If I do a quick inspection, right, 2 coppers, 1 carbon, 2 oxygens, 2 oxygens, so it's all balanced. Okay. So how the hell am I going to start this? Okay. And so now I know you're also thinking, well, Chris just told us to start with the first number we're given, and we have 2 numbers. Okay. Let's refine that rule. Start with the first measurable quantity you are given. Start with first measurable quantity. So when you say Coke is 95% carbon by mass, that's just like telling us what Coke is. Okay? So whether I have 1 gram of Coke or 1 ton of Coke, it is 95% carbon by mass. It's just telling us what it is. My actual measurable quantity is the amount that I have, the 1.0 tons. That's what I want to start with. I want to start with what I can physically put my hands on. Even though 1 ton, I could not pick that up or put my hands on that. But all the same, you get the idea, I hope. Start with the quantity that we can like measure or that we can pick up or whatever, right? And I don't expect you to have memorized what a ton is. So we look it up. We use the internet. We use our book. We look up what 1.0 ton is. And we're talking about a metric ton. I probably should have indicated that. 907.185 kilograms is 1 ton. Okay. And I also want to say, suppose if I had 100 grams of carbon, this is another thing I want you to start getting used to when you see percentages, like percent by mass or percent by volume. Okay. So Coke is 95% carbon by mass. So suppose I had 100 grams of pure carbon. So if I had 100 grams of pure carbon, how much Coke would I have? Or how much, oops, I wrote this backwards. Okay, sorry about that. I wrote this backwards. Okay, if I had 100 grams of Coke, that's a K, okay? A sample of Coke is 95% by carbon by mass. Then I would have 95 grams of carbon and 5 grams of some other crap. I don't know what it is, I don't care. Doesn't matter. Okay? So this is going to be really challenging for a lot of us to work out. Okay? So always start with what, the starting thing is, Coke. Say if I have 100 grams of Coke, what's it going to be? Well, it would be 95 grams of carbon and 5 grams of impurities. Okay, so now let's work through this problem. So I'm going to start by saying 1.0 ton. And I know in this relationship, 1 ton is 907.185. I started with this being redundant because what if this wasn't 1.0? What if it was 1.2 or 7.34 or whatever, right? So I just started that 1.0 just so I can keep track of what I'm doing. So 1.0 ton, in 1 ton, there's 907.185 kilogram. So the ton and the ton unit are canceled. I'm going to get us into the gram because hopefully you can recognize I need to get to molar mass. And to get to molar mass, I need my units to be in grams. So I went kilogram, I went down then up. So kilogram and kilogram cancel, and now I've got gram. And what is this that we're talking about? It's 1.0 ton of copper 2 oxide. Okay, remember copper 2 oxide, that's copper 2 plus, oxygen, oxide is O2 minus, so that's why it's CuO, right? They both balance. I only need 1 and 1 of each. Okay. And so when you go and calculate the mass, the molar mass of copper 2 oxide, it's 79.54 grams per mole. So I've got grams on the top, so when I go down, I need to put grams on the bottom. 79.54 grams of copper 2 oxide is 1 mole of copper 2 oxide. Okay? And now I can compare moles of copper 2 oxide to moles of carbon, because it's asking me determine the mass of coke needed to react with copper 2 oxide. I don't have coke in my chemical formula, but I do have carbon. So I can use that for my reaction. I can say, look here, right, go down. I need moles of copper 2 oxide, and I'm going to convert that into moles of carbon. So this is that step where we have to convert moles of one reactant to moles of another reactant. And my balanced reaction says 2 moles of this copper 2 oxide are going to react with 1 mole of carbon. Okay? And I'm going to keep going, folks. Let it ride. Let it keep going. Okay? And let's make sure we're canceling everything. So grams of this canceled with grams of this, and moles of copper oxide canceled moles of copper oxide. So now I need to cancel that moles of carbon. So I'm just going to put this down here and write moles of carbon, because that's what I know I need to do. And it's saying what mass. So at this point, I will use the molar mass. Okay? And the molar mass of carbon, 1 mole of carbon, is 12.011 grams. All right? This is the hard part. All right? Because now I've canceled moles of carbon and moles of carbon, but it didn't ask me for the mass of carbon. It asked me for the mass of coke. So this is why I wrote this down in the beginning, because now I can easily say, oh yeah, well, if I had 95 grams of carbon, right? Grams of carbon cancels grams of carbon. Then I have 100 grams of coke. Okay, that's hard. I realize that's challenging, and a lot of you are going to get stuck on this. If you get stuck on this, come talk to me. We'll work through it. Okay, practice makes perfect. And now I've canceled everything. The final unit I have left here is grams of coke, and that's what I was asked for. So let's calculate it away. All right. I'm going to start here. I'm not going to say 1.0 because I know that I don't need to multiply with that number. So I'm going to start with 907.185 times 1,000 equals times 1 times 1 times 12.01, 12.011, okay, equals, and then times 100 equals. Now I'm just going to leave that in the calculator, all right? And now I can say divided by 79.54, okay, equals, divide by 2 equals, and finally divide by 95. Okay, great. And that's 72,100. I'm going to express this in scientific notation, and I'm going to go, move the decimal. 1, 2, 3, 4. And so I'm going to write that as 7.2. And look, the 1.0 means only 2 sig figs. 7.2 times 10 to the 4th grams of coke needed. Now I know on that last problem, I was like, well, that was, it didn't ask me for what mass, grams or kilograms. So you were kind of free to choose. So it'd probably be logical to convert this all the way to tons, so I can compare like tons to tons if I wanted to. And so I could certainly do that, right, if I want. So this would be a fine answer, okay? But what if I wanted to compare, apples to apples, right? Well, now I know I can say in 1,000 grams, there's 1 kilogram. And in in 907.185 kilograms, there's 1 ton. And again, I know that this is redundant from what I did before, but I like to do this redundant way of calculating so I can keep track of what I'm doing. Okay? So then I could say divide by 1,000, and then I could say divide by 907.185. And I get 0.080 tons. Okay? So there's a pretty big difference in that mass. And the reason for that is because, look, copper 2 oxide is almost 80 grams per mole, but carbon is only 12 grams per mole. So that's why there was such a big difference there, right? Like if I go back to this lithium hydroxide problem, look, lithium hydroxide is about 24 grams, but carbon dioxide is 44 grams in 1 mole. But I need 2 of these for every 1 of these. So 2 times 24 is about 46. So that 46 grams to 44 grams is really close to that 1-to-1 ratio in terms of mass. It's 2-to-1 in terms of moles. But it came very close to being 1-to-1 in terms of mass because the masses of these 2 reactants are very similar. However, on this problem, copper 2 oxide is much heavier than carbon for 1 mole of that material. So that's why, for every 1 ton of copper 2 oxide, it only needed 0.08 tons of coke, or 7.2 times 10 to the 4th grams. Okay? So the last problem, I'm just going to introduce this problem, and then I'm not going to do it because we're going to do this in discussion. It's a big, scary problem, but it's related to exactly what I started talking about at the beginning of this lecture, the carbon cycle and combustion and CO2 in the atmosphere. So I'll redo this problem. And by the way, this is 2017. In discussion, I have the 2019 numbers for you. The year 2020 isn't up yet, or maybe the 2018. It takes a few years to get these numbers, but these numbers are accurate, okay? In 2017, the United States consumed 143 billion gallons of unleaded gasoline. That's for real. That's a real number that I looked up. 143 billion gallons of unleaded gasoline for motor vehicle use. Estimate or calculate the number of grams of CO2 the U.S. produced from combusting gasoline in 2017. Okay? That's what you're trying to do. How much CO2 did all of that gasoline put in the atmosphere? Right? It's a pretty simple question. Okay? If we consumed all of this gasoline, how much carbon dioxide did it put in the air? Okay? Simple question, not so simple to calculate it. So here's all the information you need to calculate that. You can assume everyone used the same grade of gasoline, the 87, that's the less expensive stuff, which is approximately 87% by volume octane. So here's like a by volume thing you have to be able to do. And all the octane was converted completely into H2O and CO2 in the presence of O2 upon combustion. So it's basically saying just assume the combustion went complete. Okay? And you need the density of octane too. Octane has a density of 0.7 grams per mil. This is a hard problem, but this is why you're in college, right? To solve the world's problems. So I don't want to waste time with doing these like worthless chemistry problems that you'll only ever see like in your textbook. I want you to be able to calculate real stuff. Like if we consume 143 billion gallons of gasoline in 1 year and only cars, right? This doesn't include boats or planes or turning the lights on, right? Charging your cell phones. This doesn't include any of that. This is just cars. This is a practical thing for you to learn and to be able to calculate. And we're going to do it. And once you learn how to do this, you're going to think that wasn't too hard. Okay, folks. I'll see you in the next video.